Good afternoon, everyone. We're Team HySol. My name consisted of Dennis Moreno, Eduardo Gorochotei, and myself, Pedro Serrat. We were originally approached by Environmental Aeroscience Corporation to develop a valve system that was reliably and safely transition a solid motor into a hybrid motor. Our timeline for this project was to end this month. We were able to develop a couple different valve systems, develop testings, static testing. We were able to do different iterations for these valves, and we're currently developing an actual prototype to fly. Our cost analysis, this is our prototype and our full scale. Our prototype cost analysis is about $1,600. It includes both the fuel costs and manufacturing for all our motor costs. Our projected output is to be able to significantly show the combination of the solid hybrid initial thrust for the solid motor transitioning into the extended hybrid motor.
So some global learning that we had to consider is like hazardous material that we're dealing with, rocket fuel, ammonium perchlorate, such things like that. All our calculations are done both in SI and in English, but in here you'll see all our units are in English. So here's our proposed design. Moving forward, we're still kind of going with this injector design. It's mostly for the big 12-inch motor that we're making. It's a two-part aluminum injector. There's 280 holes. Moving away from the taper design, we're going with just straight regular drill holing. And we're still going to have this chamber here to help increase the temperature of the nitrous oxide. So one of the things that we were a little bit skeptical in the previous design was just having fuel as a barrier between the actual hybrid, the actual solid motor, and the nitrous oxide. So we started toying with another idea where we would have a thin wall aluminum tube and it would be encased with solid propellant. And then once the solid propellant actually burns through, it would actually breach the aluminum tube and then allow the nitrous oxide to continue forward. So here's a small little SolidWorks simulation that we actually did just to have an idea of an expectation of what our failures might be. So we decided, and then we moved forward and we started making our propellant. Our propellant was H3B, that's our rubber binder, DOA plasticizer, which is a thinner to help thin out the mixture. PAPI is our curative, and we use ammonium perchlorate as our oxidizer. We had a 400 micron as our fine mesh, 90 micron as our thick mesh. And then we actually, we were playing around with some metal. We added some aluminum, zinc, and magnetic.
These are the propellant mixing procedures. The first thing you have to do is consider what the oxidizer to fuel ratio you want. Then you go on and combine the H2PV, which is the rubber binder, with the DOA, which is the thinner. After that, you add your ammonium perchlorate. You add the 400 micron first, and then after you add the 90 micron. After that, you have to make sure this is the most critical part of mixing solid propellant when you add the metallic fuel, because if you create dust, this might create sparks. So you have to make sure that you avoid creating sparks. Then you add the PAPI, which is the curative agent, and after you vacuum, wait 30 minutes, and then the mixture starts curing. This is the first injector specimen that we developed. Over here you can see our aluminum burst valve attached to our phenolic disc with a compression fitting. This is where the actual solid propellant will be. And this is the setup we use to pressure test all our valves. It was actually argon. This is the first injector testing that we did. Over here you can see the solid propellant burning, the oxidizer tank. On this side you can see that we use a pneumatic valve to make sure that we could remotely set it off. And then over here you can see that the solid propellant successfully triggered the oxidizer. These are some of our test specimens after being tested. As you can see, we're able to successfully open them. However, we did not get a consistent hole, which we needed to consistently get flow rate and to be able to characterize the motors. This is the preliminary results that we did. As you can see here, the more propellant that you have on top of the valve system, the longer it takes. So this actually helped us characterize our propellant for future tests.
Because the original injector design was inconsistent, we couldn't predict the amount of flow or the size of the hole that the burst valve produced. We had to redesign our injector valve. So what we did is, this is our injector, and it has an opening which we filled with a low melting point metal. In our case, we used bismuth. We surrounded it in the same phenolic tubing with our propellant. This is our first test for this valve. So what happens is the propellant ignites, the low melting temperature metal melts, and our oxidizer starts flowing. These are our valves for our first couple test runs. As you can see, you can clearly see our consistent diameter in our valve opening, so we can predict flow rate as well as oxidizer, the amount of oxidizer being distributed. These are our burst times as well. It's consistently increasing just as we had before. Now moving on to the next step, once we have consistent results with our oxidizer, with our valve opening, we moved on to an injector design. Our valve was opening, our oxidizer was released, but it wasn't igniting. Now the reason was because it had nothing to ignite with. So what we did was we placed our valve inside a PVC motor. Both the bulkhead and our nozzle on top are PVC as well, schedule 40. And we went ahead and tested these. We started off with schedule 40 PVC, as you can see on the left, and we moved on to a schedule 80. This one's clear. We did it so we can see the flow inside the actual pipe, see how the oxidizer is flowing within the motor. In the middle we have our dissected motor. You can see the burn pattern left behind from the burn of the oxidizer. So now that we have our actual motor, we needed to gather our data. So we had to develop our test stand. We have a vertical static test stand. This is our original design on SolidWorks, and this is our manufactured design. With our test stand, we need to gather the information. So what we did was we attached a load cell, an S-type load cell, to gather thrust. We attached a pressure transducer to gather pressure from the actual motor, and we gathered this information using an Omega DAC system. The program we used to run this was DaisyLab, and this is an example of our DaisyLab worksheet, which ran the entire program and gathered all of our data.
So once we got our test stand manufactured and ready to split, we actually had to make the motor. So the motor has two pressure ports that we lead into the chamber pressure, into the chamber, so that way you can tap off the chamber pressure. We had an analog gauge, and we also had a digital gauge that was attached that Pedro mentioned. In here we also put just a rubber liner. It was just HTBV with a PAPI to allow once the solid motor passes a certain point, it just doesn't continue anymore. And here's some of our actual results that we get. This was our actual thrust trace and our pressure trace. We were able to, this right here is just solely the hybrid part. We would ignite the solid motor would burn, and then it would ignite into the hybrid phase. We got a peak thrust of 377 pounds. We had 130 psi in the chamber. We have an impulse of 718 pound-seconds. So, and we'll go back real quick. Right here you can see there was a quick drop and there was some nozzle erosion, which leads us to our next one. Our next one, we want to try and prevent nozzle erosion. So what we did is we actually designed a throat that was made of phenolic that we glued into place. Then we covered it with HTBV, again, just the rubber liner. And what happens is that once the high velocity gases want to come out, you kind of create a convergence section. Then you will have a small divergence section in that nozzle at the end. We had a small little breach on that motor, so we couldn't continue much testing on it, so it was a very short motor. So from there, we decided to move on into the actual real hardware. We wanted something that was flight ready. So we had design parameters of a calculated chamber pressure of 500 psi. Nozzle throat size of 875 inches in diameter. That gave us a cross-sectional area of close to 1. We had a KN of 350. The KN is actually the propellant surface area versus the nozzle throat area. Due to the 500 psi, we had a due to the chamber pressure of 500 psi, we had 2,100 pounds of force on the bulkhead and on the nozzle. We had a calculated max thrust of 720 pounds. And we wanted to try to get a half-second delay between the transition between the solid motor and the hybrid motor. Right here you can see there's our rocket motor bill of materials that includes 25 components and all the testing. And here it is ready to be tested.
So you can see this is our structural design. It's composed of an aluminum casing. We have retaining rings to help the nozzle in place. Then we have our injector bulkhead, which is what carries our injector system. And then everything was held together by 12 5/16 18 black oxide flathead bolts. This is our injector bulkhead. The first thing we decided to do was to do some SolidWorks analysis. We we put heat transfer and pressure on this model to make sure that everything was correctly designed. Here you see how we manufactured the bulkhead, and here's the actual product. This right here is a program we use to create the grooves on the bulkhead and the nozzle. It also tells us what the O-ring size that we needed to contain the pressure inside the combustion chamber. This is our graphite nozzle again. We decided to go with a 7:1 expansion ratio. The reason for this was mostly manufacturability. And then over here you can see our retaining ring again in more detail. So then we go into casting the solid propellant inside our PVC cartridge. Some calculations go on in there to make sure that you cast it correctly. We figure out that we had to cast it at 237 RPMs for it to cast correctly. As you can see here, this layer is the solid propellant, and you can see here too, it's pretty uniform throughout the whole system. And we used a lathe to actually cast it. This is actually how we measure success in our project. This is the graph that shows the hybrid motor and the solid motor together. In this part right here, you can see the solid motor thrust and pressure trace. You can see the motor transition here, and then you see the hybrid rocket in this side. We obtained a peak thrust of 654 pounds of thrust, and then the max chamber pressure was 620 psi. Finally, after doing all that, we obtained a total impulse of 1,300 pound-seconds from this rocket.
So, in conclusion, what did we actually achieve in this project? Well, we were able successfully to create a pyro valve system that was reliably and safely transition a hybrid motor into a solid motor, which has never been done. This pyro valve is easily adapted into any type of injector design you want to, thanks to the low melting temperature metal. This one. The use of PVC for the hybrid motor is great because we can just go to Home Depot and just buy it and then cast it, and then we can just cartridge load them all day. It allows for a cheap solution for small scale flights, and allows for very quick iterations, as you can see. We're currently on track to submitting our report to the AIAA. We're actually going to be manufacturing a couple more motors just so that we can actually create a longer delay in between the solid and the hybrid phase, just so you can actually see that there's a solid phase, shut off, and then a hybrid phase. Currently, we're also on schedule with EAC to continue to make our 12-inch motor to break the current adventure. And up here next, we're going to have our video of all our testing, that montage of it. This is the first injector with our spool. First, we have the hybrid motor with our PVC. The next one is actually the clear motor. That was like a torch. From there, we actually go into our data acquisition. And right here, you can see what we have the nozzle loaded. And then that's our final testing. That's this motor right here. So we have a slow-mo, and I'll show you the stop to it. This is our pressure. Our cameras measure our pressure. And here is actually everything in slow motion. This is actually a post-combustion in the exhaust because we're very fuel rich. You can see the knock time is due to the underexpanded nozzle. And right around here, you'll see a transition into the hybrid. And that is that. Any questions? You want to see the video again?
No. Keep the video here.
Oh, wait, here. You want to see it?
Live,
Okay.
fine. Live action.
Yeah, I think you're all good there.
Questions? Are you going to fire a rocket now?
Yes. So what we want to do is we want to make another iteration just so we can have actual the two, because we can actually change the variance, the height of the solid propellant that we're casting, which changes the delay in between the hybrid and the solid and the hybrid. So we're trying to gather data to have actual real distinction, and then we're actually gonna make actually what they call a mono rocket, where rather than having actually an oxidizer tube, we're gonna have one whole full 4-inch outer tube that's X number long with a bulkhead in the middle. They call it floating bulkhead. So then that half will be the motor, this half will be the oxidizer tank, and then we put it on the payload section.
But this is flight ready. This could fly.
This could fly, yes, as long as obviously we cap these off and we put a check valve for fitting the tank.
Any other questions?
Can I ask a question?
Sure. Yes.
What is the record that you guys are trying to break?
Currently, I hold the record. Well, the company and I myself hold the record for 72 miles, and we're shooting for above 90.
So they have a parachute?
Yeah.
All right. Any other questions? Hearing none, thank you so much.